Okay, hi everybody. Let's start again. Um, we were talking about about both signal to noise ratio and chi-squared. Actually, you know what I should do before I continue with the lecture? I wanted to uh, ask who is working on the problem set I gave you. Some of you, I gave you a problem set on the first day. Okay, I hope you're finding it, easy until it gets hard and and worthwhile. And because it does get hard, but because it's such a integral part of what we do and we're looking for compact binaries to understand the gravitational waveform, I encourage you to go through the exercise anyway. And I also, if you run it, if you start going, this is getting hard, I can't get it right, this is going to take forever, just jump to the solutions. So, I mean, really, because in so much of what we do, we learn from what other people have done, and learning, grabbing code from other people is a useful way of developing your own, skill set through, code that you can use so that you understand. So here is the, PDF with the assignments, and here is the answer. Okay, there's the answer in HTML, and here it is in Python Notebook. And so, rather than give up completely, go and just look at the answer and understand it and read through it. It's probably worth your while. Okay. The other thing is that I'll be talking about PyCBC and GstLAL today a little bit, and these are big, complicated programs, and once again they're like canned packages. So if you run PyCBC, you'll say do match filtering on this event, and you won't be doing it yourself. You won't know what's inside that code. And so this is helping you to understand a little bit about the basics of what's inside that code. But it still is worthwhile to learn how to use PyCBC because it's been deliberately, it's a rewrite of a much, much, much more complicated code that was developed in the 90s and 2000s, over 20 years by 10 or 15 different people. It was called in those days Fine Chirp or Inspiral or something like that. And that code was written in C. It got more and more spaghetti-like, people adding things and manipulating. It's impossible to read. It got impossible to run after a while. And so the PyCBC crew said, well, we think everything is easier if you do it in PyCBC in Python, and so we're going to rewrite everything in Python. And I think they did a pretty good job of writing code and documentation for the code that's relatively easy to understand. So it is worth your while to learn how to use it if you have any interest in, doing this kind of stuff, looking for CBC events in noisy data. So what I encourage you to do is the second exercise, well, depending upon your perspective, either longer or not, depending on how much, individual amount of work you want to do. The second exercise is to go through the exercises and challenges from the LIGO Open Data Workshop that we held in March. So in March, if you go to LOSC.ligo.org, LOSC.ligo.org, the LIGO Open Science Center. Oh, you can also get to it by going to gw-openscience.org. It'll go here. Okay, so if you go to this, lost.ligo.org, and then you click on Explore the Open Data Web Course, and here you'll find videos and of talks that are given by a variety of people on all the various elements of interesting elements of gravitational wave data analysis using real LIGO data that's available. You have to set up your software, and if you set up your software, you can do it a bunch of different ways. You can either install it all on your computer in your Anaconda or any other environment that you're accustomed to. And if you're not accustomed to any environment, you can bring down an entire environment through a container, a Docker container. Okay, so Docker is just a way of getting a whole pile of software and data and even a whole operating system if you want, and putting it into your computer as a standalone container. And then you run Docker, and this tells you exactly how to do it using a Docker container. Uh, and this gives you instructions on how to download. Not just you. First, you have to install Docker, and then you have to download the Docker container for PyCBC. This one here. This step will take 15 or 20 minutes because you're downloading, or well, depending upon your internet, it's 6 gigabytes. Okay, and then you can run it. So I'm running it, for example, and I am. When you run it, the first thing you see actually is if you open up your Jupyter notebook within your Docker container, the instructions are there. It's not as hard as it sounds. Then I encourage you to actually go through. It's not in order, unfortunately, but in the instructions it gives you the order. Setup, intro, learn about gravitational wave data analysis in this nice GWPy environment, and then do the PyCBC tutorials, and then the parameter estimation tutorials. Okay, and really this will take you a few hours, and it's a few hours well spent. I mean, it's a fun thing to do. And if you click on, for example, the PyCBC ones, do them all in order. Okay, 1, 2, 3, 4, 5, and there's a challenge. Okay, so for example, here, this one, the waveform matched filter, teaches you how to generate your own waveforms from the library of waveform families that are available in the LIGO in the LAL simulation package, which I mentioned last time. You know, again, this might take a long time, but it's if you download Docker, then this you don't have to install anything. It just says it's already satisfied. And then, you're generating waveforms. You can visualize them. You can study them in for different masses and spins. You can see all the differences. You'll own it all after a while, which is kind of satisfying. And then it does some match filtering, and it actually goes through the exercise of finding GW150914, which has a signal to noise ratio of 18 in one detector. It's like screamingly loud. This is real data, and then you can visualize it and line it up. This is GW150914, the data and the waveform superimposed, and you can make spectrograms. These spectrograms, by the way, have a special name because they're not quite spectrograms. Usually in a spectrogram, this y-axis is the FFT, and it's in linear, spaced in frequency, and the basis set is sine waves. But in this case, the basis set is sine Gaussians, wavelets, Gabor wavelets, sine Gaussians. And you'll hear much more about those from Neil Cornish, because that's where he starts, is with these kinds of spectrograms. And it's logarithmically spaced. So your basis set is different. They're wavelets, and it's logarithmically spaced. And there's some smoothing going on here, some Gaussian kernel smoothing going on. And so the signal, and all of that is designed to give you a nice visual picture of your chirp as best as you can in noisy data. It's a very short chirp for GW150914. It's a beautifully long one for GW170817. Okay. But again, logarithmic scale. You see this smattering of bluish and dark blue and light blue. That's noise fluctuations. And this is something standing out, excess power, standing out above the noise fluctuations. And then at the end here is the challenge, in which you read in LIGO data in which signals have been injected. And you get to find them using all the tools from this tutorial above. It's a bit of a challenge. In our open data workshop, I'd say 2/3 of the people in the room figured out how to do it, either by themselves or with a little bit of hand-holding, and found those signals. It's really sad. They walked away going, wow, I'm a gravitational wave data analyst now. Um, and so I do encourage you to go through that, and you might find it's a very fun exercise. Okay? Okay, that was just a digression. We'll go back to talking about all the details about what's done inside of PyCBC and GstLAL starting now. Any questions though? I encourage you to do all that. Okay, back to the slides. Okay, so we talked about how the output of match filtering, which can be very efficient, can produce peaks in the SNR distribution. We use the letter rho to mean SNR. I don't even remember what rho hat is in this case. Actually, I do. It's some kind of a combination of the signal to noise ratio time series in blue and the chi-squared time series in green. And what you see is that even though the signal to noise ratio time series has a peak, it's not as sharp as this one, because this one uses the chi-squared to downweight the SNR when the chi-squared is high, but not when the chi-squared is low. When the chi-squared is low, it agrees with the SNR. For the purpose of this talk, I'm going to call it effective SNR, because new SNR was replaced by newer SNR, followed by newer, and after a while it got ridiculous, and so now we call it chi-squared weighted SNR or effective SNR. Okay? No, it's a more complicated formula, as I'll show you in a second, actually. Actually, maybe next slide. Not next slide, but very soon. I'll show you what that more complicated formula is. I mean, the point here is that chi-squared being a statistically fluctuating quantity, it could be anywhere between 0 and 2, and that's a good chi-squared. So as long as the chi-squared is less than something, you just use the SNR. But if the chi-squared is greater than something, you downweight. We'll show you how that works. Okay, and I'll restate a few things. The first thing I wanted to restate is the importance of going into the frequency domain. And of course, there's two reasons. One is that we know the noise in the frequency domain. It's not shown here. But the more important reason is because of this wonderful simplification. When you do things in the time domain, you have to do this integral once for every value of the delay. Many times. And so this convolution integral is a horrible thing to calculate. Whereas a convolution in the time domain is simply a product, an inner product in frequency space in the frequency domain. One integral instead of countless integrals. And instead you get the time series by multiplying by this quantity. And there you go, oh, well, now I have to step over the delay, t, many times. No, you don't, because this is simply an inverse Fourier transform, and you can do all of it at once and very quickly. So that's the power. It's called the convolution theorem, and it's very powerful, used all the time in engineering and physics in many different places. That the Fourier transform of a convolution is the pointwise product of the Fourier transforms. It's a beautiful result. One of many beautiful results that we use all the time in signal processing of with digital filters in the time domain, in the time and frequency domains. Okay? And here's the reminder that you have to divide by the noise, and when the noise is high, downweights the integrand. When the noise is low, that's where the integrand becomes significant. And so you end up with a signal to noise ratio. Here again, this output, which we usually call Z of t, I don't know why it's called C of t here, this output is complex. It's a time series. This template doesn't have to be normalized. But if it is normalized, then this is the signal to noise ratio, or the complex, its magnitude is the signal to noise ratio. But but if it isn't normalized, it has to be normalized, which means you would divide by H star over S integral. You don't need this anymore. And we call that sigma squared, and then the signal to noise ratio is the magnitude of this divided by sigma. And that normalizes the template so that the result depends on how loud the signal is compared to the normalized template. And the magnitude automatically maximizes over the coalescence phase, which I tried to explain last time. Does anyone want me to explain it a little bit better? Good enough last time. Okay, because this guy has a cosine-like piece plus I times a sine-like piece, and when you take the magnitude, you're maximizing over phi right there. Okay. Let's see. Oh, and what dividing by this does, this is the power spectral density, and the power spectral density is the square of the amplitude spectral density. So let's write it as the product of two powers of its square root. Here's one square root, here's another square root. Divide this square root into the template, and divide this square root into the data, which is noise plus signal. This is what we call the whitened template. This is the whitened data, and what we're doing is multiplying together the whitened signal, the whitened data, and the whitening template, and inverse Fourier transforming. Okay, and whitening allows you to visualize the signals much better, and it's really what goes into measuring the significance of a signal inside of noisy data. Yeah. Those figures, we have an interesting sociological conflict within the LIGO scientific collaboration. More than one. I'll point out one. And one is that although good physicists are both experimentalists, instrument builders, and data analysts, astrophysicists, in reality, most people in the LSC and Virgo also are more one than the other. Data analysts have no problem thinking about whitened data and whitened signals. Instrument scientists go, what is this whitening thing you guys are talking about? I don't know what it is, and I don't want to know what it is. What instrument scientists know how to do is bandpass. Just a bandpass filter will suppress all this, and only select this. You will find in our papers a mixture, because of this, just to satisfy everybody, a mixture of plots of our signal and our data, and our templates. Some of them are bandpassed, and some of them are whitened. When you bandpass, you have to do more than just bandpassing. You have to notch out through tiny little band notches all these spectral lines, because otherwise, when you look at the data, all you're going to see are gigantic sine waves at this frequency, this frequency, this frequency, and this frequency. That's all you'll see. You won't see any signal at all. So you can do it either of those ways. You can do it by bandpassing and notching, or whitening, which essentially notches because you're dividing by these big peaks. So you're essentially notching out those frequencies. And if you do either of those things, it'll make GW150914 very visible. It will not make LVT 1509 whatever it was, 151012 visible. So 151012, our instrument scientists will say, I don't believe that's a real signal. Data analysts know how to whiten, know how to squeeze the blood out of everything, which is what John Veach's talk will all be about, squeezing the blood out of these signals. And we're utterly confident that LVT 151012 is real. Okay? I don't know if that answers your question. Okay. Okay, and then an essential next step is coincidence. And of course, it helps to have 3 detectors, but you can also do it with 2. In fact, most of the time we do it with 2, but unless we have 3 detectors. And we're simply finding those, we're looking through the data, finding individually, in each detector individually, finding peaks in the output of one of our templates out of 600,000. Well, in all of our 600,000 templates, we look for peaks, and then we look for the loudest one. But we don't necessarily use the loudest one. We use the loudest combination of 2 or 3 of them from the same template, because we're going to use the same template for all 3 detectors, even though all 3 detectors have different noise spectra. So the Whitening templates are different in all 3 cases, but we still use the same templates. Now you'll recall that we calculated, I showed you how to generate a bank of templates using a PSD to calculate how close or far away the templates need to be. But if we have 3 detectors and they all have 3 different amplitude spectral densities of the noise, how do you do that? You won't get the same template in each of the 3 detectors. You'll get different template banks for each of the 3 detectors. And what we find is that, and what in general it's easy to see, it should be easy to see is true, is that the more colored the noise is, the fewer templates you need in the template bank, and the more white the noise is, the more templates you'll have in the template bank. So what we do is we look at all 3 of our detectors and say, who's got the flattest PSD? And it doesn't matter whether it's very sensitive or terribly insensitive. All that matters is its shape. Who's got the flattest one? Use that to generate a template bank, which nicely covers signals from that detector and overcovers. Oh, it's okay to err on the side of overcovering for the other detectors. And this allows us to use the same template bank for all of our detectors, which allows us to require exact coincidence, not just in time, but also in template. Yeah, either. No, you don't need to. No, you normalize it. The extrinsic parameters all drop out. We don't care what direction in the sky. We don't care how far away it is. But we do need to care what time, the time and phase at coalescence, but we take care of that with the match filtering. But all the other extrinsic parameters we ignore. And we'll figure them out in the next step, which is parameter estimation. No, Gaussian noise fluctuations will mean that this is noise plus signal. The noise fluctuations will now have units of numbers of standard deviation, numbers of sigma. So yeah, they'll be elevated from 10 to the minus 23 to 1. Of course, so will the signal inside of that. Okay, but for Gaussian noise, in the absence of signal, the distribution of this will be Gaussian, with a mean of 0 and a standard deviation of 1. Okay, and the signal will be displaced from that because it's always because it's beyond Gaussian, and the template will as well, and it'll all work out. It's elevating signal and noise, but it's elevating them more in the sensitive region and de-elevating less so in the insensitive region. And we're doing the same thing with the template because we have to, because we're trying to measure signal to noise, and unless you divide by noise, you're not doing that. This is I should have said signal to noise squared. No. just signal to noise. With proper normalization, it's just signal to noise. Yeah. Good question. Livingston currently, but I don't know what's going to happen in January. Okay. Virgo has this beautiful feature, which, let's see, this plot is an advanced LIGO plot, but Virgo has really good seismic attenuation at low frequencies. So it has lower noise at these low frequencies. But nonetheless, I think Livingston is still the flattest currently. But when advanced Virgo reaches design sensitivity, it'll be flatter, I think. Any other questions? Do you know? It's not going to be flatter? No. As a function of frequency, the flatness of S of F. Flatter. Flatter. That has two meanings in English. It doesn't matter. I mean, we got to look at a plot. Actually, we can look at a plot if you give me a second. Let's do that. Just it's worthwhile. I'm accustomed now to Ilya, like going off somewhere else. So I'll do that too. So if you look at, for example, this is a good paper to read. It's sort of a review article, and it has all these noise curves in it. And these noise curves are all superimposed. Well, maybe they're not superimposed, so we'll see. Come on. You're going to give it. This particular, this is our document control center, dcc.ligo.org. See, it says public over here. When it's this color, you can't get at it if you're not in the LSC. When it's this color, you can. Okay, a lot of our stuff is actually why isn't it? Okay, it should be telling me. P12. Oh, no, I can't find it anymore. 00087. I have probably 100 different copies of it on my computer. So let's just look at it. Right. So this is advanced Virgo now, I guess, or it's maybe here. But when it's like this, I don't know. You tell me. From 20 hertz, is Virgo flatter or is LIGO flatter? They're about the same. I don't know. What do your eyeballs say? Virgo's flatter. It's good to ask. It's good to challenge. Okay. Okay. Any other questions? All right. So coincidence is a very basic, fundamental thing. It's one of the most powerful tools in, experimental science. And here, what we're going to do is look for coincidence roughly in time. It's about 10 or 12 milliseconds between Hanford and Livingston, another 25 milliseconds, as much as to Virgo. And we're going to look for coincidence in time, in waveform, and even in amplitude and phase. That's trickier because, of course, they'll all have different amplitudes and phases. Okay, but we're going to look for some kind of consistency with respect to random coincidence of instrumental noise, which will have no meaningful information about how the amplitudes compare and how the phases compare. And I'll show you that plot shortly. So the block diagram sort of couldn't be simpler, right? Bring in data from 3 detectors, take one average power spectral density. This isn't working today. Too bad. Maybe because I don't have this plugged in. That's all right. Everything will break now. Oh, it works. That's weird. Okay. Then you match filter separately in each detector. You don't have to do it this way, but this is simpler. Match filter separately in each detector, then bring the triggers together, the peaks in the SNR distribution, and form coincidence test in time and template parameters. Okay? That's the flowchart. Let me identify a few interesting features of the second pipeline that we use. Again, we have about 4 or 5. Here's the second. It's called GstLAL, and GstLAL refers to GStreamer and LIGO algorithm library. And GStreamer is an off-the-shelf, third-party streaming digital signal processing library available. It's open source. And as I mentioned last time, if you have a Linux box and you listen to audio, you're using GStreamer. At least you used to be. I don't know if they've changed to other kinds of technologies now. Okay? So it's a natural sort of way to envision time domain signal processing. To realize time domain signal processing. Now, they use, in time domain signal processing, you're doing this convolution. It's much slower. And so it needs to be sped up through a variety of techniques. But you're doing this to reduce the latency between the gravitational wave is passed through your detector and a signal comes out of your computer saying there's something here. Okay? So you're trying to reduce the latency, and the idea was don't do it by collecting a whole lot of data, many seconds worth, Fourier transform it, and then run it through many filters, and then an hour later you've got your answer. If you do it in the time domain, the idea is that it's just constantly streaming, and you'll get your answer potentially in a shorter latency. Okay? That was the philosophy behind it. Okay? But they needed to speed it up dramatically. So they used at least 2 or 3 tricks. Trick 1 is to recognize that your template bank has many, many templates and they all look almost the same. Because they are almost the same, they overlap by 97% in our template bank. So you perform a where do I spell it out? SVD, a singular value decomposition. On this, you basically are saying that I have 600,000 rows. Each row has many, many, many columns, which is the value. It's a matrix. You then plug it into your singular value decomposition matrix solver, which is, you can get a million of different ones in LAPACK and, all these mathematical packages that you can just download, including Python and Mathematica. It'll just do it for you. MATLAB was made to do this kind of thing. Okay? This is a matrix. You do the singular value decomposition. 600,000 templates give you 600,000 basis vectors. 95% of them look like junk. They carry hardly any information at all. You throw away 90-something% of them. You say they're not going to contribute. The top 5 or so percent will be non-trivial. They won't look anything like these waveforms, but some linear superposition of them will look like every one of these waveforms to small errors. In fact, you can evaluate the errors you make by throwing away 95% of these basis vectors, almost negligible. Yeah? How is it different from having 30,000 waveforms? In the end, then, it isn't. But now you're only filtering through 30,000 waveforms and not 600,000. You're saving computer time. It's speeding it up. You can't farm this over 5,000 computers. You have to do this. You filter one set of data in one computer and another set of data in another computer. You parallelize it that way. And this SVD allows you to speed things up by 20 times. At the expense of having to add them all back together afterwards. And I'll show you how that works. Is that? Templates. Normalized templates. Notice that they're all normalized. Okay, so this is a lovely little idea. It's an idea that's been around for 20, 30 years. At first, people thought they could do it analytically. Much effort was gone into trying to do it analytically. Failed, especially when they did it for that second post-Newtonian waveform. But here's third order post-Newtonian. Oh, my whole analytic expressions fail again. Okay, so it was very frustrating until people said, well, we can just do it numerically with an SVD. Yeah. Again, you need to take um, a, a signal and run it through 600,000 templates. You have to sort of do it in one computer. And that's will take, you know, that will give you a latency of hours or something like that. I don't even know what the number is because it was way too long from the very get-go. And we realized we had to speed things up by running it through much fewer number of templates. Not only does that reduce the latency, the time between the data coming in and the triggers from the match filter output coming out, but it also reduces the electricity. You're doing a lot fewer computations. You're doing this once at the beginning of a run. That's all done at the beginning of a run. And then you use it for the rest of the run. Okay, and it did make a gigantic difference. GstLAL was sped up by a factor of 20. We knew from the very beginning that we had to do this. Another trick is multibanding. And this is also used by MBTA, which was written by the group at LSC, multiband template analysis. And they both use this particular technique, except that MBTA only uses 2 bands, and GstLAL uses 1, 2, 3, 4, 5, 6 bands. So the idea here is this. For a very long time, in a long inspiral, a long BNS or NSBH inspiral, for a very long time, it's essentially a quasi-sine wave at some low frequency, 20, 30, 40 hertz. And so why are we looking at data sampled at 16 kilohertz when all we're looking for is a signal at 20, 30, 40, 50 hertz? That means that we should have a Nyquist of like 64 hertz. We should be sampling at 128 hertz to get a Nyquist frequency of half that, and that more than covers the first minutes, many, many minutes of a long inspiral waveform. And so what GstLAL does is chop up the waveforms, downsample the data to much lower frequencies, and then all the computations, all the inner products of computing the signal to noise ratio, instead of multiplying together, let's say 16,000 numbers, you're multiplying together 2,000 numbers. Everything gets faster by that factor. So it just speeds things up by factors of 8 or 16 for most of the inspiral. Of course, when you get to the end, it sweeps to higher and higher frequencies, and then you need the full sample rate. Well, we never need the full sample rate of 16 kilohertz because Nyquist is 8 kilohertz, and we're really not expecting any signal to noise ratio at 5, 6, 7 kilohertz. We're really expecting all of our signal to noise ratio to come in the frequency band between 20 hertz and 2 kilohertz, which means we really never need a sampling rate higher than 4 kilohertz. So what GstLAL does is downsample the data. Here's the data coming in at 4 kilohertz. It's already been downsampled by a factor of 4. And then it gets downsampled again and downsampled again. Okay, according to this plot, which may be right, there's 3 bands. This band is fine for everything that has frequency content below 16 hertz. Nyquist, half of this. And this below 256 hertz, and this below 2 kilohertz. And the data get delayed by certain amounts in order to, line them all up so that the low frequency stuff is being filtered at the same time as the high frequency stuff at higher sampling rate. That's what all this stuff does. Oh, that's what all this stuff does. So here we're doing we're doing downsampling, which in GStreamer is like a stock, highly optimized piece of code that you download from the internet. It's a highly optimized, been developed by signal processing engineers, many of them professionals. They all get paid a lot more than we do. Just going to use their code. Okay. For downsampling, whitening. This beast over here is now adding up different bits of the signal to undo the SVD, to do the inverse of the SVD, to reproduce the original templates from the basis vectors that you've been filtering through. With suitable delays, they all get added up to get signals, signal to noise ratios. Finally, all these, well, these are early warning outputs, but when you finally added them all up together, you get the output of one real template as opposed to the basis vector templates, and you've added properly all the multi-bands. I'm explaining all this with a block diagram. Maybe you're getting some of it. The code does all this. Does anyone have a question to help if I'm not explaining it terribly well? It's never easy to explain this. But anyway, multibanding and SVDing in the time domain to reduce the order of the problem, and multibanding to reduce the number of multiplications you have to do in a time domain filter. That convolution filter, many multiplications, is reduced dramatically when you do it at lower sampling frequency. The combination of those two things speeds up the time domain convolution computation by factors of 100 to 1,000. Yeah. Oh, yeah. Right. 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 So this multibanding is guided by the template, not the data. The data has whatever the data has in it. Okay. And then you are downsampling the data, but you're also sampling the data at the highest sampling rate that is of interest to us. And you're running that through the parts of the template that require it. And only those parts. And you're not going to run it through this part or these parts because you don't need to. You can run that through that part. And then it gets added together. It gets all added together coherently because you know in advance how the template adds up with proper delays. Does that help? Okay. So those are some of the neat little innovations of GstLAL. The fact that we're using a lot of stock signal processing tools that come from third parties gives us some sort of confidence that it's been debugged and that it's supported by thousands of people out there. The flip side of it is, I don't know what this code does. Somebody else wrote it. I'm not sure I can trust it. I have to test it in 1,000 different ways. But that's what we do. Now that's for small stretches of data, and of course when you have large stretches of data you need a plan, and so we have a simple plan. You take your long stretches of data, you only consider the ones that are in which data from Hanford is in coincidence with Livingston and or Virgo. So you only look at coincident times. And but we don't. We look at all times, not just coincident times. But really in the end we're only going to be worried about coincident times. Yeah. Give signal detector triggers. That's right. That's right. So now we're going to generate signal detector triggers. as well. Okay, so here's a single detector science segment. What is a science segment? An earthquake happened over here. The entire detector was down for a while, and then we bring it back up. And when we bring it back up, we have to bring it into lock. And as Peter Salson told you, bringing things into lock is not so easy. It took a long while. Does everybody know what the words bringing into lock means? It sounds like you do. Is anyone not? Well, I'm going to explain it. Okay. All right. So remember that Stefan told you, and maybe Peter, I wasn't there, about how to control a Fabry-Perot optical cavity. Did anyone talk, did even Stefan talk about Pound-River Hall locking? Nobody talked about Pound-River Hall locking. Well, I could, but I'm not gonna. But the basic idea is that the mirrors are on pendula, and they're swinging in the breeze, if there was any breeze, in a vacuum chamber. Anyway, the mirrors are swinging there in a pendulum, and the laser light is going into the input test mass. The laser light is going to the input test mass. 99% of it is being reflected. When it swings into resonance, then this light, the little bit of it that gets through after a round trip, interferes constructively with itself and with the fresh incoming light if this distance is exactly or very close to exactly an integral number of wavelengths of the laser light. The laser light wavelength is 1 micron. Very close to an integral number. And when that happens, you get a strong flash of decrease of reflected light because it's stored in here for a brief moment. But it's swinging in the breeze. And so a moment later, it's gone. That's called a Fabry-Perot flash. Usually, you can set up Fabry-Perot cavities such that they become transmissive when they hit resonance. You know, for those of you, I'm digressing here, but it's worth doing it. And for those of you who don't appreciate this, understand that this mirror is 99% reflective, and this mirror is 100% reflective. But let's say it's 99% reflective. So this mirror is 99% reflective, so is this one. Here's a mirror, 99% reflective. Hi, I see myself. Here's another mirror. It's also 99% reflective, and it's behind the first one. Okay? But when they're exactly an integral number of wavelengths apart, or a half integral number of wavelengths apart, so that the round trip is exactly an integral number of wavelengths apart, I can see right through both of them perfectly. The transmission goes to 1. Optics. Optics is cool. Now that's an extreme version of what your anti-reflection coatings are on your glasses. Okay? But it's a tool we use all the time. Anyway, for that brief flash, the reflected light peaks. I can call it an airy peak, but it isn't. It's a Lorentzian. But anyway, if in a Pound-River Hall type experiment, you set up a method of measuring not the power reflected, but the amplitude reflected by beating it against a local oscillator. And when you do that, you end up with a Pound-River Hall signal, which is linear in one very small region. Here's another peak. First free spectral range, second free spectral range. This is something Stefan or Peter should have told you all about. Right over here is the one we're operating at. Linear control system to tell us how to push back on the mirror to keep it in control at resonance in lock. Okay? Its problem is not that simple, of course. We have Fabry-Perot optical resonator here, a Fabry-Perot optical resonator here. They're both inside of a Michelson, which is inside of a power recycle Fabry-Perot optical cavity, and a signal recycling. Two Fabry-Perots inside of 2 other Fabry-Perots. Damn complicated. Learning how to actually, as they swing in the breeze, again, there's no breeze, you're in a vacuum, but they're swinging around uncontrolled. Lots of signals are coming out. There's a signal coming out this way. That's called the reflected port. There's a signal coming out this way. It's called the transmitted port. Sometimes this is called the symmetric port and the anti-symmetric port. Sometimes this is called the bright port. This is called the dark port. All three of these things all mean the same. And signals coming out here. And there's even a signal that comes out here in so-called pick-off in the power recycling pick-off, whatever. Anyway, they're all like signals flying around all over the place. And the computer's looking at all those signals and going, what am I going to do next? What am I going to do next? And then you teach the computer to do the right thing and learn how to control everything as these things swing by. It's hard. We have lots of helping. We have auxiliary lasers, all kinds of things to help. But we do this. And then we reach lock, which means that all of our servos that push on the mirrors to keep the resonance condition are in this linear regime. And again, this linear regime is a very tiny fraction of the total signal. So you gotta find when you're here and then try to stay here. It's hard, but we do it. Does that make sense? All digression. We were out of lock. We came into lock. Everything was shaking like a leaf. The mirrors were going like this because they've just been kept under control. We fell out of lock a little bit later. This is called the lock stretch. It might be, well, Peter Solson told you that the first time we achieved this, it lasted 2 seconds. Then we got it up to 2 minutes. Then we got it up to 2 hours. And sometimes this can run for 2 days without falling out of lock. Quite more and more often. Virgo is probably even better because Virgo has really good these super attenuators. So you could probably stays in lock for days. We chop it up into half-hour blocks. I like to round things up, round things around. The half-hour blocks, and we overlap them. And we know that there will be startup transients. So we overlap beyond the startup transients. And then at the end, we may not be able to fit a whole 2046-second block, but we do it anyway and throw all this away afterwards. Okay. And in each of these blocks, we do our match filtering. In fact, even within those blocks, we chop it up into smaller pieces. And what we used to do is compute a new power spectral density and a new template bank for every damn one of these. And now we don't. We use the same template bank for days and days and days. And we overlap them all. Because if the signal goes from here to here, you won't see it in one of these short segments. You'll see it in the other. We do one other cute thing when we're doing power spectral densities, noise curves, and that is that when we do noise curves, let's see. So Marianne mentioned the Welsh averaging. That is to say, we chop the data up into small pieces, calculate an amplitude, calculate a Fourier transform squared here, 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 and then average them many times. So we reduce the statistical fluctuations. And the averaging that we do is bin by bin in frequency. So at every bin in frequency, we take a noise spectrum from here, 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 an FFT, from here, 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 and here, and find the average. And then we do another average for the next frequency. And we don't do a mean average, we do a median average, which means that if there are any big noise fluctuations or signals, as long as they don't show up in more than one or two of these segments of time, they don't affect our averaging. Signals do not throw off our power spectral density estimations because we do median averaging, not mean. If you looked at one frequency bin and you had 10 measurements of the noise in that frequency bin, or 100, let's say, measurements, and you looked at their distribution, they should probably be distributed Gaussian, unless there's a signal. And if there's a signal, you get this long tail. And maybe in both directions. But if you're doing median, you're basically finding the middle. It's closer to here than to here. And these guys do not throw off the result. If you're doing mean averaging, these guys can totally screw up the result. A loud enough signal would totally screw up our noise estimate because it's not noise, it's signal. But not with median averaging. Bin by bin and frequency. Oh, you're right. Which is why we have lines. Which is why we have lines. Exactly. Okay. But at least if the lines are instrumental, we can predict them and we can subtract them later. Yes, but in O3, the calibration will cancel all those lines. 97% of the way. No, we can do that. We can do it. Okay, so this is how you analyze months of data by chopping it up into smaller pieces, running it through the match filtering algorithm, looking for triggers, and then looking for coincidence, and then writing all those coincidences out into an output file. And in the end, the output file just tells you, I found something with some template, may not be close to the real one, but it's some template, and it's at this moment in time. And all you really need is the moment in time. And later, you can go back on the data and analyze it much more carefully, as John Veach will explain next week. Okay? Okay, that is the filtering, and now we have to do two important pieces. We have to extract signals, okay, and we have to, and once we've extracted signals, triggers that are coincident between detectors, we need to estimate our signal efficiency, which we'll measure by our sensitive volume or sensitive distance to which we could detect a signal above our thresholds, and our background, efficiency and background. Okay, those are our next steps. First, background. Let us assume that the dominant or perhaps only noise sources in our background, and by background we mean, oh well, this is what we mean, are instrumental noise fluctuations that are non-Gaussian, really loud, glitches, but that they're uncorrelated between the two detectors. Because the detectors are far apart, hopefully, except for the two detectors we built at Hanford. Now there's only one at Hanford. We used to have two at Hanford in the early part of the 2000s. And there was a problem that they saw the same disturbances and therefore the background was correlated in time between the two detectors. But otherwise, if they're separated, let's assume they're not correlated in time. There are mechanisms that could correlate detectors separated by thousands of kilometers. They include lightning strikes and the like. Lightning strikes, for example, anywhere in the world might produce an electromagnetic pulse seen in two different detectors. But like I said last time, our environmental monitors are much better at picking those up than our detector, which is engineered to be as isolated as possible from them, are. So if we don't see them in our electromagnetic pulse sensors, then we're pretty sure they're not in the data. And so far, we have never observed a coincident signal caused by an environmental disturbance like an electromagnetic pulse. It's never happened. Instead, it's local environmental stuff, and that isn't going to be correlated. Now, a lightning strike will produce maybe any electromagnetic pulse in two detectors, but it'll also sort of ring up the electromagnetic field between the surface of the Earth. That's a pretty bad Earth, but what are you going to do? Surface of the Earth and the ionosphere, okay, some kilometers up, which reflects electromagnetic energy pretty well, which is good because here's an antenna and here's a radio, and oftentimes you get really good reception even though you're very far away because the radio waves bounce off the ionosphere. This forms a cavity, a spherical cavity. A lightning strike over here will generate electromagnetic radiation which resonates in this cavity. I forgot how many kilometers up the ionosphere is. You can look it up, and if you do that and then do a simple engineering calculation, you can figure out what the frequency of those resonances are. 100 kilometers, divide by the speed of light, add a geometric factor of 2, 8 hertz. 8 hertz, 16 hertz, 24 hertz. Those are called Schumann resonances. And they will produce correlated noise all over the world. These are global resonances, electromagnetic resonances. They might be a problem for us. So far, they haven't been. Remember I said that we usually start at about 20, 25 hertz above the Schumann resonances. We monitor them with very, very sensitive magnetometers. Super sensitive. These magnetometers are so sensitive that the only way they can detect Schumann resonances is if you take them and drive 10 miles away from anything, bury them in the ground, walk back to your car, open up the door, get in your car, close the door. It registers that loud and clear. You close the door on your car, these magnetometers go, whoa! And then you drive away and you leave them alone. And they are pretty good witnesses to Schumann resonances. So we monitor them. But they're all at low frequencies, and they just, so far, haven't bothered us. In the future, we have to worry more about them. There was a question. Yeah, Faraday cage. Well, guess what? Our vacuum chambers are Faraday cages. So we do our best. They're not perfect Faraday cages. There's nothing like perfect in this world. And if you're trying to build the most sensitive measuring device ever, you run into the imperfections of anything and everything, including the Faraday cages that are our vacuum chambers. They're not perfect. Things get in. We measure it. We measure a transfer function. It's pretty small, but any small thing messes us up. Anyway, so under this assumption, we can then take here's like a random noise glitch that rings up a detector, a match filter for one of our templates or 50 of our templates. In fact, glitches will typically ring up all of our templates. Here is our template bank, M1, M2. Here's all of our templates. A signal over here will bring up this template a lot. And remember those ambiguity ellipses? It'll ring up these templates a little bit less, and these templates a little bit less, and these templates a little bit less. And it probably won't ring up these templates very much at all because they're different frequency content. Okay. A glitch is a delta function. It has all frequencies. It rings up everything. So you can tell a difference between a loud glitch and an extended quasi-sinusoidal signal, a chirp, just by looking at the distribution of the SNRs across the template bank space. It's a tool we can use. All right, anyway, you've rung up some templates here, you've rung up some templates here at some random time, and so on. And we want to estimate the probability of getting accidental coincidences or anti-coincidences or something like that. And so we simply time shift the data. We time shift the L1 data by this. Oh, this guy lines up here. I got a coincidence. It's accidental. Shift a little bit more. Now these guys line up. That's an accidental coincidence. We can study their properties. We can see what their signal-to-noise ratio and chi-squared and all these other things are. And say, okay, if this passes all of our cuts, it's our background. And we can do this time shift 1,000,000 times. We got 1,000,000 seconds of data. We shift by 1 second each time. There's no way gravitational waves would survive that. When gravitational waves are coincident, 1 second shift, they're not anymore. They need to be coincident within milliseconds. So we get many, many, many instantiations of accidental coincidence, 1,000,000 of them. That allows us to extrapolate our background curve to 1,000,000th of an event. Okay. The background, fortunately, is not so badly behaved. For Gaussian noise, if you plot the signal to noise ratio versus the number of events, the log of the number of events, for Gaussian fluctuations, fluctuations of Gaussian noise, ringing up our templates, you get a distribution that falls exponentially. Actually, it falls like e to the minus rho squared, maybe over 2, maybe not. I forget. I always forget. Because there's 2 degrees of freedom, cosine and sine. Something like this. What about the signal? Signal does not have an exponentially falling distribution, I hope. Okay. Let's see if I can do this off the top of my head. Otherwise, I'll just pull an Ilya and say, I apologize. But off the top of my head, if the rate goes like the volume, which is the luminosity distance cubed, and if the signal to noise ratio goes like 1 over the luminosity distance, because it's an amplitude, the amplitude falls off like 1 over luminosity distance, okay, then the rate is proportional to the number of events. So let's see if I can do this. dn should go like 3d squared d r 3 r squared dr, and rho is 1 over r squared dr. So dn by d rho, maybe this is right, dn by d rho goes like 1 over r to the 4th. Oh, sorry. Goes like r to the 4th, which is 1 over rho to the 4th. Did I get it right? Close enough? Here's dn d rho to the 4th power. An exponential falls like this. This doesn't fall so flat. Well, that's good. Signals could stand out over the noise. That's the only way you can detect in this world, if the signal stands out over the noise. Yeah. Yeah, the chi-square does that. And we'll use it in other ways as well, which John Veach will tell you about. The signal morphology, once you do a full parameter estimation and you fit it to the best template you can, not just one in your bank, but the best template. You've looked over a parameter space finely with a Markov chain Monte Carlo. Then you get a Bayes factor, if you're doing it Bayesian, which tells you this signal looks like the correct morphology. And you can use that instead of rho as your detection statistic. The only problem is that we can compute the signal to noise of a signal in the LIGO data in fractions of a second, but it takes fractions of a year to do it with parameter estimation. So we have far less statistics. Anyway, here you detect very confidently. Here, not so confidently. This was LVT 151012. This was GW 150914. And here you're utterly buried in the noise because this rises exponentially. And all the work is squeezing out the last bit of this. All the work is squeezing out the last bit of this to improve our sensitivity by a factor of 10 or 20%, okay? Which is a volume increase of 3 times that, 30%, which is only $100 million worth of funding for your detector. That's where all the work goes. This is with 1 template. Here's with 2 templates. It's twice as big. Here's with 600,000 templates. It's 600,000 times as big. But the thing is falling so quickly that it only ruins our sensitivity by a small amount. That's why you always win in match filtering, even if you have a lot of templates. Yeah. Instead of it falling like this, it goes like this, or maybe this. That's really bad. You got to work hard to get rid of that. I spent 20 years on that. Managed to get rid of most of it. Almost all of it. At least for low mass systems. But for high mass systems that look more and more like glitches, it gets harder and harder and harder to do. Okay? Anyway, this is how we estimate our background, this distribution, and we can even do it to estimate the tails. And you'll see some tails in a minute. In fact, will you? Let me skip a few slides and go back to them. And okay. So here's our exponentially falling background. Here's this 1 over rho to the 4th, sort of flattening out because we only have 3 or 4 events here. And here is a tail, and this is an even longer tail. What is this tail? It's not glitches. This tail is that guy, and when we estimate the background, using this method I just sort of briefly described to you, that guy is here, and now we do some time slides and something else lines up with it. That long tail is signal making believe it's background, because we're assuming that everything is background when we do these time slides, but it isn't. Sometimes there's signal. And if the signal is really loud, it creates this gigantically long tail, which fortunately goes away if you just remove this guy. If you just remove this guy, all of this goes away. We just remove the triggers associated with this guy. Here's this long tail, a better measure of it, long tail. Okay, notice that it's really a small number of events, like less than 1. The background prediction is much less than 1 event, because this guy is only introducing 1 trigger in 1 detector that gets time slid in accidental coincidence with glitches. So these are glitches in accidental coincidence with this guy, and it happens rarely, once in 1,000 time slides. Okay. Then we remove this. When we remove, we say this is an event, a detected event. Darn it, it's not detected. Okay, I'm not even touching you. Okay, so this guy is a signal. Once we've decided that he stands out over the background, these things are called, this is called the big dog. This is called little dogs. And if this ever extends way out to here, these are called rabid dogs. But we don't have any in this case. So if you have a really loud glitch in coincident with a trigger from this guy from one of the detectors, that would be a rabid dog. Fortunately, we don't see any in this case. So we decide this is an event. We remove it. We remove it from the background estimation. That leaves this. And then we repeat, because this second event is producing this tail. And it's now background to itself. But it's still loud enough that we can declare its signal and remove it, and left with this. And then our third event, it doesn't matter whether we've removed it at all or not. Does that make sense? It's not easy to estimate the background in non-Gaussian noise. You have to do it from the data. You can't do it from any analytical or numerical way. You have to do it from the data. Yes. This is all of them. Anything that will ring up any of our 600,000 templates loud enough. Above a threshold of a signal-to-noise ratio of 4 or 5, something like that. Well, the background is glitches. And the foreground are real events, and these happen to be all BBH. Haven't yet considered estimating the signal efficiency for NSBH. But there's no NSBHs in this plot. Well, there probably are, but they're very faint. We don't see them. They're buried in the noise. If they weren't buried in the noise, you'd know about it. Does that make sense? Stop. Yeah. Hierarchically start removing the little dogs. I've got them using this silly thing. Okay. Here's LVT15. Okay, this is 2 sigma. That's why it's got an L. But this guy is darn close. It's 4.5 sigma. I'll take it. Actually, according to this, it's less than, sorry, it's about 4.5 sigma using this background estimate, and it's way more than 5 sigma using this one. So this is a Nobel Prize. That's 5 sigma. Okay, you're doing your Higgs analysis. You got a 4.9 sigma isn't good enough. Okay, you need 5. After that, who the hell needs 5 sigma? We know BBHs exist. This is 4.5 sigma, good enough for me. What you're really doing is computing the false alarm probability. If you ask a statistician, a false alarm probability of 10 to the minus 5, isn't that low enough? They'll go, of course it is. But if you ask a Nobel committee, they'll say it's not. Yeah. Exactly from this plot. Just read it off from the plot. Okay? This is normalized carefully. You can see it agrees with the background. The foreground, the glitchiness in the foreground. So that's a good important check. That's got to be normalized correctly. And then you just read it straight off. That's the false alarm probability, which is good, but it changes when you take more data, because you now have more data to analyze. So what you really want to do is divide by the observation time to get not a false alarm probability, but a false alarm rate. Okay? So a false alarm rate doesn't depend on whether you took data last week or you're going to take data next week. It's just it's a local measure. And that local measure we have a threshold on that, which is if a false alarm rate is 1 false alarm per century, fantastic. 1 false alarm per day, no good. 1 false alarm rate per month, I'm going to tell the astronomers about this. It may not be real, but it's good enough to tell astronomers, because then it means if you have a false alarm rate of once per month, it means you'll only be bothering those astronomers once a month with a garbage background event. And that's, they can tolerate. We ask them, can you tolerate that? They go, oh yeah, you can bother us once every week, but please, not every day. Okay? Okay, so okay. Here is something that we call a blip glitch. 10 hertz, 100 hertz, 1,000 hertz, 1/10 of a second, 1/5 of a second, 1 second. It lasts, this is 50 milliseconds, it lasts a few milliseconds. Where does it come from? I think it comes from scattered light, but I'm not sure. Picowatts of scattered light scattering out of the detector and back in, right into that photodetector, and just a picowatt of a photon, just a few photons is enough to create something like this. There's no way of watching for that, of monitoring that. There's no environmental monitors. There's no microphones or seismometers or magnetometers are going to find any of this stuff. Okay, there's no witness channel. It's only in the DARM H of T strain data. What we'd like to do is get rid of glitches by finding a witness. And the witness will say, this is coincident with an electromagnetic pulse that's coming from Mozambique's having a lightning storm. Then good, we'll reject it. But sometimes we just can't do it with our auxiliary channels of monitoring. So instead, we have to do it based on the H of T data itself. So instead of vetoing this based on some witness that says you've got junk here, we have to get it from the signal itself. This is called a signal-based veto. How are we going to veto this guy? There it is. Here, it rings up this template. It doesn't really. The chi-squared is going to be lousy. It matches this template. It rings up this template, but now we got to get rid of it. So how do we get rid of glitches? first thing that we can do is not only require coincidence in template, so it has the same morphology or rings up the same template with a large enough SNR, but we also require it. The time difference can be as much as plus or minus 10 milliseconds between Hanford and Livingston. But we don't know where it is in here, but we know it's not going to be 14 or 15 milliseconds or minus 14 or 15 milliseconds, the other way around. Furthermore, the phase, which comes from maximizing the cosine-like and sine-like parts of the template bank, you find a coalescence phase at Hanford and Livingston should be within about a half of a radian, plus or minus. That's our accuracy, about a half a radian. No, this is 0.5 pi, whatever. That's about it's about how well we can do. Mostly, you see, our signal is, coincident. It's within pi or 0 times pi of each other. And so, if our signals are inside of this region, which we've painted up through simulations of signals, then we say, hey, it's coincident. It's consistent with being signal. And if it's out here at large time differences or large phase differences, we know to reject it. Either reject it or down-weight it in its signal significance. It's our detection statistic. So, essentially, we're looking for coincidence in time, amplitude, phase, and signal morphology, masses. That's our first step. The next step is our chi-squared. We chop the waveform up into regions of equal contribution to the total chi-squared. Maybe looks like there's 1, 2, 3, 4, 5, about 10 or 15 bins here. Here's the Fourier transform. We can do it also in frequency domain, which is what we do. We do it in the frequency domain because that's easier to figure out its contribution to SNR because we know the noise as a function of frequency. We don't know the noise as a function of time. We chop it up, construct a chi-squared, and as I said before, the chi-squared will peak just where, this doesn't show it, the previous plot did, the chi-squared will peak just as will dip just as the signal-to-noise ratio will peak, and a combination of them will give you a better detection statistic than signal-to-noise ratio alone. So if we plot signal-to-noise ratio, this happens to be a log scale, versus chi-squared, which is also a log scale. Okay. Very high chi-squared, forget it. These are clearly not signals. Throw it away. Okay. The colored stuff is I'm sorry, this plot is hard to read. There are sort of reddish, brownish, reddish crosses here. Those are loud injected signals. This one happens to be GW150914. Really loud. Signal noise ratio like 30. Okay. And chi-squared on the order of 1. The background from time slides is all this black stuff here, which dominates here. Low SNR, low chi-squared. We throw away all the high chi-squareds, but there's still, we could throw away more of them. Work harder and throw away more of them. We're afraid to do that because the chi-squared for a signal that has a lot of precessing spin, when matched against a filter that doesn't include precessing spin, might have a lousy chi-squared. There's a signal over here, way over here, close to this. Okay? Dangerous, dangerous, dangerous. We're getting close to the background here. So we construct these simple contours. These are really loud, effective SNR or new SNR or chi-squared weighted SNR, which just becomes SNR if the SNR is less than 1, if the chi-squared is less than 1. This is lower, lower, closer and closer to the background. So we use these contours to define this chi-squared weighted SNR, which works better than simple SNR because it uses more information to separate signal from background. And that's our effective SNR or chi-squared weighted SNR detection statistic. GstLAL does something even fancier. It makes a two-dimensional histogram and draws from it, and produces a likelihood ratio of signal to noise. Same thing. Okay. Oh, and this is just an example for 150914 of how the SNR peaks loudly, the chi-squared dips dramatically, and the chi-squared weighted SNR peaks to the same level because the chi-squared is 1, so the chi-squared weighted SNR is going to peak at the same place, but it's narrower. It's narrower. So we get better timing and more confidence. And as a function of time, the real data looks like this is a blow-up of 50 milliseconds around, and here it is for 10 seconds around. It really stands out in Hanford and Livingston. Okay. But we still have those blip glitches. They ring things up when our template is really, really short, which corresponds to really, really high mass systems. So we still have this, but in those high mass systems, they merge at 100 hertz. The high mass systems merge, in this case, at 80 hertz. So this template stops here. But the blip glitch is broadband, and it has frequency content at frequencies of way higher frequencies. So we're going to take little sine Gaussians and say, do I see something here, 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 and here, and construct another chi-squared. This should be close to 0, but it isn't for a blip glitch. And so we can suppress blip glitches with this blip glitch killer. Clever idea that Alex Nitz came up with a year or two ago, and it's pretty effective at getting rid of the background, the long non-Gaussian tail, even at relatively high masses. Oh, we never ran it in 01 because it was invented between 01 and 02, but now we have gone back and reanalyzed 01 with this. It's cleaning things up a fair amount. Yeah. And I better end. So I'll just end with we rank the candidates, and we have to verify that our signal efficiency is good. So we do that with injection campaigns. We inject 1 million signals covering the parameter space, and make sure that we identify the ones that are close enough that we should be identifying them. Okay? Our usual rule of thumb was a signal with an SNR of 8 or greater is going to stand out pretty well. We'll be able to detect it. Turns out, with all of our hard work, we've got that down to about 6.5 or 7. Signal to noise ratio of 6.5 or 7 in one detector. We can, with 2 detectors, detect it confidently. So we were being a little overly pessimistic by assuming we needed SNR of 8. And so I'll just end with this slide. Here's one of the many dimensions of our parameter space, not many, chirp mass, mass ratio, and align spin. So here's one of the dimensions of our parameter space that we're covering with our templates. Here are several million injections. The vast majority of them were, if they were found at all, they were found with a very high false alarm rate of 10 to the 3 per year, or 10 to the 4 per year. Okay. These are not found. These are found with lower false alarm rates, and these were found with low enough false alarm rates that we can call them detections, the blue guys. And it's plotted against this quantity, which is essentially how far away the signal is. So if the sorry, not how far away the signal is, the expected SNR. The expected SNR. And the expected SNR just comes from, here's how loud the signal is, and let's calculate the average SNR that you might expect from an average of many instantiations of the detector noise. That's quick to calculate. You'll be doing it in the problem set I gave you. And what you see is that we start detecting at an SNR of around 7, 8, 9, 10, of around 7, reliably. I don't know what's wrong with this guy. He only has a false alarm probability of 10 to the minus 2, but he should be found with false alarm probability of 10 to the minus 4. So often what we do is we zoom in on one particular injection and say, hey, what happened here? I mean, literally, we look at every one of these, not every one of these, the weird ones, okay? These guys down here that are found even though they shouldn't have been. You know what these are? The ones that are found even though they shouldn't have been? We injected them right on top of glitches. Son of a bitch. Anyway, and this guy would probably had a glitch nearby that ruined the chi-squared. Almost always, it's a glitch nearby. Okay, I'm out of time. And so I would like to thank everybody for your attention, and I'd like to encourage you to do those 2 sets of exercises. The first set that I gave you on the first day, and then take some hours and go through the open data workshop tutorials. I promise you, you'll learn a lot. If you like data analysis at all, or even if you don't, you might start liking it, especially when it's all being done for you before your eyes and you're learning, and it's worth your time. Okay, so thanks everybody for your attention.